Hello and welcome everybody to a new video. So if you've been following along with my channel for the last 6 months or so, you'll know that for a good bit of this year I have been teaching myself some Rust. So this week I'm taking a little bit of a break from the robotics project that I've been working on for the last while, and I decided that I would go back to doing a little bit of Rust, and for that I'm implementing this little project that we're going to look at today. So the project that it is today is we're going to look at implementing Conway's Game of Life. So if you've not heard of Conway's Game of Life, don't worry, we'll go through it now. We'll run it, we'll see what it looks like, and we'll go through the code. So this is going to be pretty similar to my Advent of Code videos, if you've watched any of them. So yeah, let's just jump straight in. Let's look at the problem and let's talk about the code. So let's have a look at the problem. So I shouldn't really say it's a problem as such, as it's kind of framing this the way I do the Advent of Code videos. It's really more of Conway's Game of Life is basically a simulation. And so we're going to look at the simulation, how to set it up, what it looks like, and yeah, how the code works. So this is the wiki article for Conway's Game of Life. You've probably seen something like this before if you're into this kind of stuff. But basically, it's something like a cellular automata that's done in 2 dimensions, and it follows a really simple set of rules. So if you don't know what a cellular automata is, don't worry too much about it. But basically, it's sort of like a simulation that's based around something that resembles like cells and living organisms and how they work, obviously in a much more simplified fashion. So you basically take some initial state of cells and you apply these rules to them, and you regenerate the state over and over again based on the rules, and you end up with patterns like this. So this is something you can end up with. You also end up with stuff like this. And yeah, that's pretty much it. So you start off with some initial state of cells that are alive and dead, and then you apply these rules to them, and then it generates a new state, and you keep doing that over and over and over again until you get to some end state. You can run it for as long as you want and see what you get out of it. There's some states that will just die off completely and they'll just end up with nothing, or you can end up with like these steady states where nothing changes every time you run it over and over again, so in which case it's finished. And you can also end up with these infinite states that will just keep repeating and oscillating over and over again. So yeah, that's basically what we're doing today. We're gonna make this. Okay, so let's have a look at what the actual rules to set this up are. So uh, we can see here this is doing stuff, this is doing stuff, and they're pretty complicated things that they do, but they're all based off of these really 4 simple rules that are written out here. So simple rules. First one, any live cell with fewer than 2 live neighbors dies as if there is no population around it. So if you have just 2 cells side by side and you look at either of those, you count the number of people around it, there's going to be nothing, or there's going to be this is less than 3, so you count the population in the area. If it's going to be less than 3, then basically nothing happens, or they all just die off, so nothing happens in the next generation with them. Next rule, any live cell with 2 or 3 live neighbors lives on to the next generation. So if you've got basically 1, 2, 3, 1, 2, 3, 4, then you'll live on to the next generation. And then you've got any live cell with more than 3 live neighbors dies. So this means that if you've got 1 cell in the center, and then you've got like 1, 2, 3, and then a 4, something right beside it, so that block, then you'll die. So nothing will happen to the next generation. And then the last one is any dead cell. So dead cells in this case would be like blank cells that have nothing in them. Any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction is what they say here. So through these rules, you can get all of these mad patterns emerging, which is pretty cool. So they're very simple rules. They don't really represent. They say like, John Conway was a mathematician and stuff, and like they sort of say that these things are like they're kind of like biological systems or whatever. They're totally contrived. They're not really. They're just more of a curiosity than anything. Okay, so with all that said, those rules, let's have a look at how we can do that. Well, first, actually, let's run it. So I have it set up here, so I can run my own simulation of it, written in Rust. So if I run cargo run, it'll run my code for it, and there we go. So this is my simulation running here. You can see these are our stable states, these little ones that aren't moving at all, and you can see the rest of them that are still propagating, and this will probably run for a while. It's different every time because I have like a randomizer that randomizes the state. You can see there's a bunch of these like stable states have been reached where nothing else is going to happen with them, no matter how many oscillations you do or how many generations you run. And you see here, this example here, this little dude here, he's just going to keep oscillating like that forever. Same with these, and then these are kind of moving around. And you can see as some of these travel, they'll interact with these other static ones or the other oscillating ones, and they'll sort of kick off into new wild patterns. This one hasn't settled down yet. It's going pretty strong. This is pretty cool. I'll try to see if we get one of these ones that's going to keep going forever. There's these like traveling patterns that will just move across your map basically forever. And no, that's gone static now. So you see here our population number down here isn't changing, but the generations are changing, so we're still going. These oscillate around. The total number doesn't change, hence why the population number isn't changing. But that's completely static in a stable state now, so it doesn't matter how many more times I run this. I run the loop, it's just going to keep going like that. So we can kill that there. But yeah, that's basically what the whole thing does. It's not terribly interesting, but it's kind of cool. Okay, so with that said, let's have a look at the code and see how that works. Let's see. Yeah, okay, so this is our code. This is a single file of Rust. It does all the work. It's just about a little bit over about 120 lines long. And there's a handful of functions in here that make some stuff easier. But the bulk of everything is done in this one loop in here, which pretty much does the whole thing. So let's walk down through it and let's see what it does. So we start off with our grid. So you see this is basically a grid pattern that we're interested in. So we need to model that grid somehow. Now, the kind of naive approach to doing this, or the simple approach to doing this, is, well, it's a grid, so you just need a two-dimensional array, and that basically is it for your data structure. If you have watched my Advent of Code videos, you'll know that I'm not a huge fan of that. And with Advent of Code, you'll also find that very often a way of making the problems more complicated is that the first part of the problem you might be able to model the whole two-dimensional array, and then the second part of the problem he'll say basically add 1 billion to each row, and then you won't be able to do it anymore because it's just going to be far too big to store in memory. So with that in mind, one of the ways that I like to approach this is to create sort of an infinitely scalable data structure, or a data structure that's more likely to scale to much larger numbers. And for that, I use a hash map. So the advantage of using a hash map is a few things. You can, if you create a key so you create your key for your hash map is a unique coordinate system. So in this case, it's just I use like x:y as like a string key for it that's unique. And what that means is that I can store each coordinate as a single entry into the hash map. You've got continuous time lookup efficiency for looking up any key because it's a hash map. And the real key to this, the real crux of this that simplifies it, is that you don't actually have to store every single cell. So if this is like a 60 by 60 grid, you don't have to store, 1,200 points or something. All you need to store is the wait, that's not right. What's 60 by 60? 3,600. No, you do your maths, Ian. 60 times 60. Yeah, 3,600. You don't have to store 3,600 points. You only need to store the number of points that you have that are the live cells, in this case represented by the hashes. The reason you do that become apparent as we go through the rules a little bit later on. But yeah, you don't actually need to store all of the dead cells or all of the empty cells. The reason being that they'll just kind of waste time, because most of the time the empty cells that have nothing around them, they don't do anything anyway. the only empty cells that are important are empty cells that are adjacent to live cells. So you don't need to store everything. You don't need to iterate through everything. You just need to iterate through all of the live cells and the dead cells that are adjacent to other live cells. And then you can actually make all the logic work. So I'll go into that anyway in a little bit of detail in a second when we go through the actual rules being applied. So first thing we do, we create our grid, which is going to start empty. We define our area. So this, what you see here is actually just the grid is infinite sized effectively. There's no cap to the size of this, bar much you can store in physical memory. But I'm only printing a 60 by 60 slice of it. So it is possible when I run this that the generations will just keep going and you'll end up with some traveling artifact that will just keep going. It'll go off the screen here, but it will continue in memory forever because it's just an updating coordinate in the hash map. Doesn't actually change anything. So yeah, anyway, that's just so that it's easier to visualize. I just visualize a limited grid of it. So first thing we need to do is we need to seed our grid. So I can look at that. It's not super complicated, but basically what I do is I just take the grid as it is. I generate 2 random x and y coordinates, and then I stick in 3 points around that grid. So what it does is this basically creates a point and then one above and one to the right, or whatever way the camera way that lays out, but basically just creates 3 points all together to seed it, and it does that 35 times. So it creates a little block of 35 times and just randomly fills it into the grid space basically to have some seed, and then that's what we use to kick it all off. So yeah, that just creates the 3 spaces, and then the thing we do here is we store inside the grid all of the neighboring coordinates to each of those points. We store a 0 into each of those. So we have this function down here, which you just pass in an x and a y, and it just generates the keys for the points all around it. So that is like, so it stores this point, and then it stores that one, and this one, and that 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 one. And that is just your lookup, so that you can easily look up all the neighbors of any given point if you provide its x and y coordinates. Just a little convenience method. So yeah, we loop through each of those. We check if the grid contains that coordinate already, and then we insert a 0 into it. So 0 in this case is a dead cell or an empty space. So not in the array, or 0 means nothing, means dead space or empty cell or whatever. Okay, so we do that, we seed our grid, and then I print it out on the screen, which just gives us our first frame of the animation. And then we start into our main loop, which is just an infinite loop that will continue to run until we kill the application or kill the program. Set our generation to 0. So we start with generation 0, meaning nothing has happened yet, and then that will increment as we go on to give our little generation counter down here. So now we're basically into the guts of the actual rules, and the entirety of the rules pretty much that define how all this works are these 2 if statements down here. And that's basically it. These 2 if statements control all of the logic. But we can go through this code anyway just to see what it does. So first thing, basically what we want to do is we need to iterate through every point that's stored in our grid. Remember, every point that's stored in our grid are all of the live cells, so the ones, and all of the adjacent dead cells or empty cells to those live cells. So that's all that's in our grid. We can start some stuff off here. So the first thing we need to do is, so we're going to loop through all the keys of this hash. So to loop through the hash, what we do is we just pull out all the keys of the hash here into a vector, and then we're just going to loop through that vector of all the keys. And then we're going to use that to get the values out of the hash. So we do a first lookup here to get the value. So this will either be a 1 or a 0. So a 1 for a live cell, 0 for an empty cell that's adjacent to a live cell. From here then, we need to pull out the x and y coordinates. We do that by doing this split logic and then this map function over the key, which is just a string. So remember I said that our format for our key, which you can actually see it down here, it's x colon y. So if we just split that string out, we can get the x and y values out of it. So we do that here, and we end up with our x and our y coordinate. And then what else do we do here? Yeah, so we need to also then pull out the adjacent cells to that, so we know we have our x and our y. So then we need to get our adjacent lookups, which we do, which gives us this NB chords list. And then we can calculate this population value. So what the population value is for any point here, it is just the sum of the live cells within this. So the maximum value this could be is 8. So if we're on a cell and we go, this one's populated, if all of the adjacent cells are populated, then it would be 8. You don't include the one that we're on. Well, I'm not including the one we're on. Doesn't really make too much difference, but you could include it or not. Doesn't matter. You just see where it affects the logic down here. And that gives you the population. So the population is effectively, it's this logic. So the amount of neighbors that it lives next to is effectively the population number. So you look at all the neighboring cells, and then the amount of those that are live are the population number, is what I'm calling it. So have a look at that. So we've calculated our population, and we know whether the current cell we're on is live or dead, and that gives us everything we need to know to figure out the rest of this. So you notice that there's only 2 if statements here that I've said do all the logic, but there's 4 rules that we saw. The key to this is that only 2 of those rules make a cell live in the next generation. So the other 2 rules make sure that that cell will die. A cell dying means you just don't do anything with it. But the cell living is what makes you update the grid for the next generation with that cell in it. So that's sink in for a second, but yeah, there's only 2 rules there that make something live and 2 rules that make it die. We only need to implement the ones that make it live for the next generation, because by default, if the cell is empty or 0, it's dead, so we don't do anything with it, so we don't need it. And we can see that here if you look at the rules. Any live cell with fewer than 2 neighbors dies. So this is one of the death rules, so we don't need to do anything with that. A live cell with 2 or 3 live neighbors lives, so that one is a live cell, so that counts. And then any live cell with more than 3 neighbors dies, so again that's a death one, so we don't do anything with that. Now the last one here, any dead cell with exactly 3 live neighbors will come to life, so that's a living one, so we need to do something with that. So we have 2 rules that make things live in the next round. One is if it's a live cell, it'll continue to live. The other one is if it's a dead cell, it'll come to life. So those are the only 2 rules that we actually need to implement any logic for to handle. And we do that here. You see we have, this is the live cell case, this is the dead cell case. And then the only thing that changes what that happens is this population count. So for the first one, if our population is either 2 or 3, then it's fine, then it works. So we then insert 1 into that key, and then for all of the cells around it, we don't do anything, or we insert zeros for them if there's nothing in there already. And then the final case is the dead cell case. So we have 0, it's dead cell, and if it has exactly 3 live cells around it, we know it's going to come to life. And we do the exact same thing here. We insert the 1, and then we insert zeros around it if they're not present in the hash already. And that's it. that's the whole thing. That's all the rules. It's pretty straightforward. Now, if it's not immediately obvious, the part I mentioned earlier about why we only store the dead cells that are immediately around the live cells, it's because of this check here. So we don't need to know about these cells all the way out here, right? Because if you read the rules, the only cells, dead cells, that will ever come to life are the ones that are next to a live cell already. And because of the way we do this thing, where we store the cells all around it, we only need to care about the ones that are adjacent to the live cells. So they're the only ones we need to check. Because if it's adjacent to a live cell, that's the only way it could come to life. So by storing the live cells and all of their adjacent empty cells, then we know which ones we need to check. It's a little bit of an optimization there. If that's not super obvious why that works, just think about it a bit, and it should come to you. But yeah, that's the real trick here, to be able to cut down the size of the data set. Um, so like in this example, that really doesn't matter. Like I said, it's 60 by 60, so it's 3,600. Really doesn't matter. Like that's not going to take that long to compute. But if this was 100 million by 100 million grid, that's a very different game to try and store all of that data, especially if it's a very sparse data set. So a sparse data set would mean that there's far more empty cells than there are populated cells. So you saw down here, the population is 126, but we know that there's 3,600. So that's a very small percentage of cells that are actually filled, which means it's a very small percentage of cells that we actually care about the data that's in them. So this way of storing them in the grid is far more efficient. Yeah, so that's pretty much it. That's pretty much how it works. It's very straightforward. Down here, the last little bits I do down here, so I copy the grid. So I had created a new grid down here, which is where I was storing the next generation's values. So we just override the old grid with the new grid. We do a clone operation in here just to copy the data over, increment the generation, and spit out some. We wipe the screen clear so that we can print some more lines, and then we just print out the totals here. The print function itself that I'm using, it's just basically just print lin. That's it. So I just combine the data. If it's a 0 or not present, I put in a dot. If it's a 1, I put in a hash, and just print that line by line, and then just clear the terminal to get it to do a thing. It's very cheap little visualization animation, terminal animation. There's nothing fancy there, so just to show it off, really. And yeah, that's pretty much it. I did write this in Ruby as well, so I don't yet, because I'm still kind of only learning Rust. I don't quite think immediately in Rust, but to solve these types of problems, I often need to quickly write something or debug it and check it. And Ruby is a very, very quick language for me to do that. And I think Ruby is very well suited to doing that kind of stuff. So I actually wrote this in Ruby first, and then took my implementation from Ruby and rewrote it into Rust here, to try and do that mapping in my own brain to teach myself. But the Ruby code is actually very, very similar. Basically the exact same structure, have a few functions that do the same things. And in terms of length, it's 90 lines long. And my Rust code is 120 lines long, so it's about a third bigger. But also Rust does have more boilerplate in it than Ruby does, so they're very, very, very similar in the amount of code that's actually in them. In terms of performance, it's kind of difficult to say the performance, because I do have thread.sleeps in here basically to make it sleep between each rendering on the screen, so that it's not just a big flashy mess and you can actually see what's happening. But this Rust code would be probably marginally faster than the Ruby code. It's not doing anything wild, so I'd say both of them will perform pretty well. But yeah, the Rust code should be a little bit faster. Okay, so that's about it. I didn't really want to go into any more detail with this. It's pretty simple. It's pretty straightforward. I hope this helped explain it to you if you were trying to do this yourself. I hope this explains what the algorithm does and how it works a little bit. Feel free to ask me any questions in the comments. I'll do my best to answer. I'm always conscious when I do these programming how to show up videos, it can be a little bit rambly. But yeah, it's kind of more my stream of consciousness and how I think about stuff that has come out. But anyway, I hope you liked it. I hope you enjoyed this video. And yeah, I think we'll leave it there, and I'll see you guys in the next one. Oh, and I have to say the code is in the link in the description, so if you want to see my code for doing this, check it out in the description. All right, we'll leave it there. Thanks for watching, guys. I'll see you in the next one.